All right, welcome. So in this video, we are going to return to our most favorite theorem, the invertible matrix theorem. And we're going to add some additional, or at least one additional statement to that theorem. So recall that invertible matrix theorem, I think we're up to about letter O or so in terms of listing all of the equivalent statements that we have to saying that matrix A is invertible. So we're going to add a condition to that list relating to the eigenvalues of a matrix. So let's recall some facts before we add our next statement to the invertible matrix theorem. So first of all, recall that 0 is going to be an eigenvalue of a matrix A by definition if and only if there's a non-zero vector x such that ax equals lambda x. Okay, in this case, our lambda we're saying is 0. So 0 is going to be an eigenvalue of matrix A if and only if ax is equal to 0x, which is equal to the 0 vector, regardless of what x is, right? If I take 0, the scalar 0, multiply it by matrix x, we get the 0 vector. So we're going to have 0 as an eigenvalue if and only if we can set up the characteristic equation to say that 0 should equal the determinant of A minus lambda I. And so if lambda is 0, then this matrix that we're subtracting from A is the 0 matrix. So we would get the matrix A back. So now our condition for finding if 0 is an eigenvalue of matrix A, that's going to occur if and only if the determinant of matrix A is equal to 0. And so this condition, determinant of A equals 0, is one of the statements that we have in the invertible matrix theorem, in the sense that if the determinant of A is equal to 0, we've previously shown that that's equivalent to saying that therefore A is not invertible. And let's take a look at some of the other statements in this invertible matrix theorem. And so from this previous bullet, we see that lambda equals 0 is going to be an eigenvalue if and only if the homogeneous matrix equation AX equals the 0 vector has a non-trivial solution. And from the invertible matrix theorem, this tells us if the homogeneous matrix equation AX equals 0 vector has a non-trivial solution if and only if A is not invertible. So now we can see A not being invertible is equivalent to determinant of A equal 0 is equivalent to 0 being an eigenvalue of the matrix A. So therefore, we get that A is going to be invertible if and only if 0 is not an eigenvalue of the matrix. So we can add this statement. This is now up to R, so we still have some letters left. We're running out of letters for this invertible matrix theorem. But now we can add this statement that says, well, A is going to be invertible if and only if. Now we have another way to test this, which is if we find the eigenvalues of matrix A and 0 is not an eigenvalue of matrix A, then we know that A is invertible. If 0 is an eigenvalue of matrix A, then we know that matrix A is not invertible. Okay, and let's take a look at another really nice general result that we can prove. We can illustrate it at least with the following example. Let's say I want to find the eigenvalues. In this case, we have a 6 by 6 matrix A. And notice that this matrix has all 0 entries above the main diagonal. So this is what we would call a lower triangular matrix, since all of the entries sit on or below that main diagonal. And if we want to calculate, or we want to find the characteristic equation for this corresponding matrix A, then recall what we do is we take a look at the matrix A minus lambda times the 6 by 6 identity matrix, which would wind up subtracting lambda from each of the diagonal entries and not doing anything to the off-diagonal entries. And then we're going to go ahead and calculate the determinant of this matrix to get the characteristic polynomial. And we've proven already that for triangular matrices, upper or lower triangular matrices, the determinant of these matrices are simply going to give us the product of the diagonal entries. So in this case, our characteristic equation would be that since the determinant of a minus lambda I equals the product of these diagonal entries, so in general, when we calculate this characteristic polynomial for this 6 by 6 matrix, we'll get a degree 6 polynomial. And finding roots of degree 6 polynomials is not trivial. But in this case, when we have a triangular matrix, such as this one, the determinant is going to simplify to just the product of the diagonal entries. So in other words, our polynomial is going to come in factored form. So the determinant of a minus lambda I in this case is 1 minus lambda times the factor 3 minus lambda times the factor 5 minus lambda times the factor 9 minus lambda times the factor minus 5 minus lambda times the factor 1 minus lambda is equal to 0. And so we can see here that the solutions to this characteristic equation are lambda equals 1, 3, 5, 9, minus 5, and 1. So this matrix A has 5 different eigenvalues, namely 1, 3, 5, 9, and minus 1, with eigenvalue 1 having what we call multiplicity 2, because its factor in the characteristic polynomial occurs to the second power. And so this is a really nice general fact that follows for any triangular matrix A. That is, if we want to find the eigenvalues of a triangular matrix, and here we used a lower triangular matrix, and the same applies for upper triangular matrices, then the eigenvalues of a triangular matrix we can get from just looking at the diagonal entries of that matrix. What I mean is the entries on the main diagonal of that matrix. So here we can see it was 1, 3, 5, 9, minus 5, and then 1 occurred with multiplicity 2. And to carefully define what we mean when we refer to the multiplicity of an eigenvalue, this is the multiplicity of the corresponding root of the characteristic equation of A. So in this case, this characteristic equation had a double root for lambda equals 1. So we would say the eigenvalue lambda equals 1 has multiplicity 2.